So now it goes. So even for fermions, we have this superconductivity, and it's really the current can circulate forever. And I think the experiment they made, there was this for 2 years, and then it was some strike, and then electricity was braked, and the cooling system stopped working, and therefore superconductivity was destroyed by temperature and not by some other effects. Okay. So let me kind of start with specifying what actually we are studying. And as a theorist, if you open the theory paper, the first formula is the Hamiltonian. Yeah? So, but a few words before, what we will study here is a set of, let's say, n particles, identical particles. In a box with a volume V. Yeah. So, and of course, in the end, we will mean the thermodynamic limit, where you set both m and v to infinity, but as an interesting limit, of course, we want to keep the ratio, which is concentration, fixed. And of course, particles, I will specify they're marked by their positions. In the simplest case, yeah, structureless. But typically, we'll also have for bosons, we'll consider bosons without internal degrees of freedom, so it's therefore just position. And for fermions, of course, we will need spin or analog of spin quantum number, which specifies, you will see, and you probably most of you know, you need at least 2 species of fermions to have interaction between them in the regimes that we will consider ultra-cold dilute gas fermions. So, and of course, now we write the Hamiltonian of the system we want to study, and it has 2 terms as usual. The first one is a single particle term, which is, okay, let me open the bracket, minus h bar squared over 2m, where m is the particle's mass, and then comes Laplacian, acting on the position of particle I, plus, which we not consider in this lecture, but in experiments, it's very typical situation, trapping potential. Of course, if you have trapping potential, you don't need a box, yeah, and you don't have thermodynamic limit. Yeah? So you have a fixed number of particles in a trapping, but we don't consider trapping potential. Plus, of course, the most interesting part is the interaction. Half sum over I not equals j, v ri minus rj. This is interparticle potential, and very often I will call this the first part H0. Yeah. For those who knows the perturbation theory, I hope you do, all do. And this part is either H interaction or simply V. And very often I will skip this hat that denotes the operator. Hopefully it will not create problems in misunderstanding of what I'm talking about. Yeah. So let me now, so this is the problem we want to study. But before I start writing some more specific formula, let me specify some relevant parameters such we can specify the regimes we are working in. Yeah? So what are the parameters? Of course, relevant. From the particles, so particles, we have this concentration. Yeah, and here, of course, I write this for the simplest case of just a single species. Yeah? Concentrations of particles gives us the average interparticle distance, yeah? Or mean interparticle distance. Let me call it n minus 1/3. Yeah? In a 3-dimensional case. Yeah? So this is mean interparticle distance. Or separation. Yeah, so it's average distance between the particles in your gas or in your system. Second, of course, we cannot avoid temperature. Yeah? In most of the cases, temperature. And this gives us either a typical thermal kinetic energy, yeah, we know, so therefore we have typical momentum, yeah, thermal momentum of particles. Let's talk about for a moment bosons. Fermions will be a bit more complicated. And so that gives us a thermal momentum, which is, I'm not writing this factor of 2, this is square root of m times t, and I put always k Boltzmann equals to 1. H bar will be there, by Boltzmann constant I skip. Yes, I measure temperature in energy units, but in experiments you measure it in whatever units you can imagine. So well, let's make not this life complicated. And therefore, using this thermal momentum, I can define lambda t, which is h bar over pt, or it is h bar over square root of mt. This is de Broglie wavelength. Yeah, which is somewhat wavelength associated with this momentum, with the motion, kind of particle wave dualism. So this is from the wave part. And finally, important for us would be, of course, something that relates to the last term, to the interaction. Yeah? And here, so interaction V gives us what is important for our case, range, A0, interaction range. I do not consider the charge systems or dipolar system where this kind of range is. But for the van der Waals interaction, interatomic interaction, this is relatively good defined phenomenon. Huh? So this is the range beyond which the particle interacts. If the distance between them larger, then they don't. Yeah? So now, with all these parameters, let me specify what does it mean ultra cold, what called first gases. What does it mean? Gases, so regimes we are in is, first of all, what is gas? Gas is when the A0 is much less than interparticle separation. Yeah, clear. Yeah? So most of the time particles do not interact, and then in these rare moments when they come in a distance with a relative distance A0, they interact. Yeah? Interactions are rare. That is what we normally assume as a gas. Huh? And a second, of course, what we need, this is a gas. What means ultra cold or cold? Meaning that the thermal de Broglie length is actually larger or comparable with interparticle separation. And this is also means that you are in the regime of what is called quantum gas. Quantum gas. Quantum gas. Because for the classical gas, it's opposite. Yeah? So classical, just to write it here below, because I cannot write there any way sort of conveniently. So Boltzmann or classical gas is when lambda t is much smaller than this interparticle separation. So here atoms really look like classical objects. Yeah? And here they start knowing about their quantum origin, whether they are bosons or fermions. And this is the very interesting regime to walk in. And yeah, so that's exactly two regimes, two conditions we will consider. Yeah? So let me now discuss how, so this is very general Hamiltonian. Yeah, V of R is complicated interatomic potential, but in this regime, what we are dealing with here, it turns out that from this potential we need to know only one parameter. Yeah? So in this case we can simplify. Yeah? Interaction. So if you look more carefully at these conditions, yeah, for example, this one, and related through the momentum, yeah, this is actually means that h bar over p, typical p, is larger of the order n minus 1/3. Yeah, if you look very carefully, if you compare these conditions and these conditions, yeah, you will immediately find out that what we have is, if I multiply this typical p, t, with R0 divided by h bar, yeah, so I have this one and I have this one, and you think a little bit, so it's equivalent that this dimensionless quantity, yeah, is much less than 1. And those who know very well, I mean, has a serious course in scattering theory, yeah, because the atoms, they scatter with each other. Yeah? And I think Anna Maria will give you later this week course about scattering. Yeah? She will definitely talk about this one, because under this condition is called low energy scattering. Low energy scattering. And the advantage of this low energy scattering is that it's only S-wave scattering is efficient. So only S-wave scattering. The other P wave suppressed by a factor PT R0 over h bar squared. This is P. If you compare S scattering with P wave scattering, or for bosons D, we have to consider even worse. Yeah. So all the other channels are very small, and you can neglect them. So therefore, we have only S wave scattering. So therefore, the only parameter therefore we need from this V, no matter how complicated it is the S-wave scattering. S wave scattering. And maybe in the lectures I will just use just A. I don't have lattice, so will not be confused with the lattice spacing, which is traditionally also called A. Yeah. So in my case, AS and A would be the same. So it's S-wave scattering. That's the only parameter which you need from the interaction. Yeah, you measure it in experiment or calculate theoretically, and then it's the only entrance that you need. So therefore, in this regime, we can replace this interaction with a simplified form, G times delta function R1 minus R2, where this G is 4 pi h bar squared over m times AS. So therefore, that's the most simple form of the potential. Yeah. And we will use this form. It's in this regime. It's legitimate, but one has to be very careful, yeah, how far one should go. Very often it's called pseudo-potential. Yeah? And pseudo-potentials are designed in such a way that you see, so here you have true scattering, true S-wave scattering. Yeah? So it's a result of from the theorist's solution of the Schrödinger equation in all its beauty, etc. But here it looks like it's already the first order in the perturbation theory gives you AS, the full solution. The first order contains kind of the full solution. So therefore, that actually means that with these pseudo-potentials, you are not allowed to go beyond the first order. So it's designed in such a way that the first order gives you the full solution for the scattering. In these lectures, twice, we will have the situation where we have to go to second order. Then you have to remember that actually what stays here is not the true potential, but what is called bare potential, and we will need a kind of renormalization procedure to go back to the scattering amplitude from the bare interaction that you have here. Sorry for these highly theoretical words. Yeah. Another kind of hint why one should be careful if one goes beyond the first order is that if I have a scattering on a delta function potential in 3 dimensions, who knows what would be the answer? Of course, I can consider quantum mechanical problem. I have a delta potential, and I send the particles. I solve the standard scattering problem with a delta functional potential. Who knows what the answer is? What is the answer? Do you have a scattering theory in your quantum mechanical course? Yes? Probably this you will never consider. Yeah?
I'm not completely sure, but I think it's like no interactions in 3D.
Absolutely. Absolutely. So delta function in 3D doesn't scatter. So if you replace delta function with this kind of potential, finite range, finite width, and then you take a proper limit, yeah, the amplitude of the potential to infinity, width to 0, such that the integral is finite, yeah, V0 times A or R0 cube is finite, then you get that all your scattering phases go to 0. So it doesn't no scattering. So therefore, if you have this potential and try to solve the problem honestly, it's just ideal guess. There's no potential. So therefore, be careful. Be careful. So when you have potential like this, that means first order only. Don't go to higher order. Because if the referee will ask you what happens in the higher orders, of course, it's a provocative question because he knows that nothing should happen. Yeah? So please be careful. We will have 2 places in the lectures where this becomes important. Okay, so now we know what we are doing, what the Hamiltonian we have to solve. So let's now come back to the quantum mechanics. Yeah? So how do we solve the problem? Typically in quantum mechanics, we're looking for the wave functions. Yeah? So we're trying to solve this, the Schrödinger equation where you act, why am I writing? On all these wave function, again, I write here for simplicity just structureless particles. Yeah? They don't have spin, but the spin generalization is clear. You can just introduce, instead of R, psi, which is a combination of R and sigma, and write here instead of R psi. And then stationary, if you are more or less thermodynamical or stationary things, we're just looking for the stationary solutions. And plus, of course, boundary conditions. So in our case, you can impose periodic or 0 because box is very large, so it should matter. Of course, if you are in a trap, the wave function should go to 0 at infinities. Yeah? So plus boundary conditions. Yeah? Boundary conditions. Yeah? And this psi depends on many variables. And of course, the psi is not only has to be the solution of the Schrödinger equation, but it has to satisfy the proper symmetric properties. Yeah? So psi has to be either symmetric, fully symmetric for bosons, or anti-symmetric for fermions, according to the exchange of whatever pairs of particles you have in this wave function. And this, of course, limits you, because again, provocative questions on a test, if I solve this, find psi, is it a physical wave function for many-body system of identical particle? The answer is yes, if it satisfies the proper symmetry conditions. Yeah? And you understand that, of course, for 2-body problem, 3-body problem, this is the way one can follow. Yeah? But if you have million particles in your trap, or infinite, many infinite of very, so writing the wave function is not very productive. Yeah? Unless you have some guiding mathematical principle that shows you what is specific form of this, like what people do in fractional quantum Hall wave functions or so. Then you can try to write wave function and see how good they are. Yeah? Actually, not solving Schrödinger equation, but optimizing the parameters. So this is not the proper way, or at least this is a possible way. And how would we do it if we would follow this? Yeah, of course, we have to start with this H0. Yeah. And we have to find out the basis, yeah, because there are so many parameters there, and the idea is, of course, whatever you do, you just expand in a single particle wave functions. Yeah. So, so therefore, these are building blocks, are single particles wave functions. These are solutions of this H0 Hamiltonian. Yeah, because you see each part in here, or maybe not H0, sorry, it's not H0, the ingredient of H0. In our case, this is simply minus H bar squared over 2m. And in general, I can write here plus U on R. Yeah, and here I forgot the Laplacian. We don't have it, but I can write formula in a more general case. Equals and acting on some phi nu of R, yeah, equals epsilon nu phi nu of R. Plus, of course, boundary conditions, yeah, for the trap or whatever for the box. Nu is a label, quantum state label. In our case, for the box, in the case of the box, nu is just P, momentum. Huh? Or in the case of fermions, sigma I, or sigma, sorry, sigma, the spin projection that labels our single particle quantum state. Yeah, and what we know, if we solve this, so we know that this sum of the wave function, the phi nu, form a complete basis. Yeah? So any solution of this equation can be expanded in terms of this complete set. Complete means that I will assume that they are normalizable. I will use these formulas afterwards, that's why I want to write it, and form a complete set. Complete means that I have performed now the sum of a nu, phi nu of R1, phi nu of R2, and somewhere I have to put the complex conjugate. It gives me Dirac delta R1 minus R2. So, and in principle, now I can, if I have many particles, I can construct the many-body wave function. Yeah. So, how can I construct now the many-body wave function for non-interacting particles? If I would have v equals 0, the simplest case, how would I construct the wave function? Okay, I just, no, probably I should write there, because v is 0. How would I construct the wave function? Of course, it depends on all these coordinates. But now I have to specify each particle in which quantum state it sits. Yeah? So I have here nu1, etc. nu n. Yeah? And I just have a product of I, phi nu I are I. Yeah? So I know these particles in a state whatever, ground, this is the first excited, this is the fifth excited, etc. And make a product, and then and this would be solutions of many-body Schrödinger equation. Sorry, in this case, free particles many-body equation. Yeah? There's no interaction, so many-body is a fiction. But I have to come now to this point and symmetrize it. Yeah? This is a product, but then I have to apply to it either symmetrization operator or anti-symmetrization operator for bosons. Yeah? This is anti or symmetrization operator. And then the result would be my physical wave function, which satisfies my free particle Schrödinger equation. And of course, the energy in this case would be in this state, sum of I epsilon nu i's. So this is non-interacting case. Yeah? So now with interaction, of course, let me put here 0, yeah? Just meaning V0. So V non-zero, we know it's the whole combination of all these elementary, let's say, wave functions, yeah? So in this case, psi R1, etc., is just a sum over C, let me put it like this, nu i's, and here is this psi 0, all these nu i's, and here R1, etc. And this, the Schrödinger equation determines for these coefficients, etc. So you see this is kind of heavy job to find out. And it sort of requires a lot of writing because these wave functions are big and the coefficients are typically nasty. So it's not the way to go. So for this, treating these sort of problems, it's very convenient work not with this position-dependent wave function, but with the occupation of the quantum state, single particle quantum state. Because if you have a symmetrized or anti-symmetrized wave function, meaning you have identical particles, there is one-to-one correspondence between occupation of these single particle quantum states and this form of the wave function. If you give me occupation of the quantum state, I can immediately construct you this wave function, positional space. So therefore, people work in this wave function, so to say, language in these quantum states and their occupations, not in terms of positions. And this language is called second quantization. Yeah? So now some second quantization. Who had a course or at least lecture, one lecture, two lectures on second quantization? Very nice. So I can just limit myself to a very basic formulas that I need. Yeah. So of course the very basic formulas. So now we have kind of walking in this Fock state. So we have to order our quantum states, FIPS, etc. These are quantum states, and of course the element, let's say phi 0 or whatever, is just the wave function in this occupation number state. This tells you how many particles in the state nu1. This is nu2, etc. Yeah? So for bosons, all n's can be from 0 to infinity. Integers for fermions only 0 and 1. Yeah? So if I know this one, or let me put here this now n's. Yeah? So this is one-to-one correspondence to this. Who wants, I can present the explicit construction. Yeah? There is an explicit construction for fermions. It's Lottie determinant. For bosons, it's a bit more exotic sums, blah, 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 factorials, etc. Yeah, but there is one-to-one correspondence. Occupation numbers, the wave function. Yeah? And of course, we know that the basic elements in this Fock space are a set of operators. Okay, a nu dagger. This is creation. So it goes nu and nu plus 1, and annihilation operator. And nu goes into n nu minus 1. Yeah. Depending on Bose or fermionic, bosonic or fermionic case, you need algebra. So you need either, okay, sometimes people write plus minus. Okay, let me write it in this form. Nu1, nu2, dagger plus minus. Plus means anti-commutator. We come later. We start with the commutator. This is delta nu1, nu2. And the other, whatever, is 0, and that's corresponding for dagger. Yeah, and there is, so these are algebra that sort of defines for you transitions between these states, all the states. And there is a unique state which is called vacuum state, 0, which has no particles at all. Yeah? So that means it's annihilated by all annihilation operator. Yeah? No particles. And then you start populate this state by applying this. So for example, if I have a bosonic case, well, actually, I guess it's in a general, I can write this formula. So for example, this state is just, I have to have the vacuum state. Yeah, and then I have the product. Yeah, and then I have a nu dagger to the power n nu divided by n nu factorial square root. That would be exactly this state. So you see, n1, the new one, I populated n1 times, n2, n2 times, etc. And this takes care of normalization. Yeah. And of course, the main formula we must write, which we will a couple of times use, is how to translate operators written in the momentum representation, in the position representations, into the secondary quantized representations. Yeah? Yeah. Okay, so transformation of operators, and then that would be probably the last formulas for this of operators. So if a single particle operator, let me call it H1, which is sum over i's, all particles, H of Ri, some operator acting on position of just a single particle. For example, what it could be? It could be either our Hamiltonian, and maybe, which we don't have now, or it can be momentum operator. So you see here I don't write I, yeah, because I have here R. Yeah, so clear. You can have also, if you like, delta R, okay, R minus R. Yeah? And if I have it like this, that simply tells me what is the density at the position capital R. Yeah? Then what happens, how can I translate this into the secondary quantized form? Or maybe I should remove here H, well, I don't know. So H now, second quantization, yeah, it's a very simple formula. Sorry, how to translate? I forgot. You have to introduce field operators for this. Yeah, probably I should write it first, but let me, yeah. Okay, let me finish with the operators, and then I just write how to translate. And of course, there are two body operators, which, for example, our interaction. Okay, let me put here H1. Yeah, and now let me put H2. That depends on our positions of two particles. In principle, not necessarily the difference, but typically it's difference. Yeah? Translation invariance, etc. But here it doesn't matter. Yeah? So in here example, of course, H2 1 R2. Yeah? So here I have two variables. It's just our V R1 minus R2. That sort of operators, the basic that we need. Yeah? Somehow we're dealing with. So how we can translate? We have to introduce what is called field operators, which is also kind of object on their own. Psi of R is sum over nu, A nu, this is this A nu, phi nu of R. Yeah. Let me write here box, our box V. When you have a box, momentous are discrete over very dense, if the box is very large. And in this case, my phi nu of R is nothing but phi p of R, which is 1 over square root of volume. I just take normalization to 1. Exp ER over H bar PR, plane waves. Yeah. For large box, the boundary condition doesn't really matter. So let me just take a plane waves here. So I just rewrite this field operator in the box in the following way: 1 square root of volume, sum of a momentum AP, e to the I over H bar PR. And we need the conjugate, psi dagger, which is, of course, the conjugate. And again, in the box, it's 1 over square root of volume, sum over P, AP dagger, e to the minus I over H bar PR. This is a strange object. Yeah? They are operators in this space, yeah, because it's A and A dagger, with the coefficient which are position dependent. Yeah? So these are operators in the Fock space of this state. Yeah? Because they have operators A and A dagger, so they change occupation numbers. Yeah? But the coefficients depends on our positions in space. Yeah? That's called field operators. Field, because it depends on the continuum variable. Operator, because it's operator. Yeah, so very natural name in this case. Yeah? And let me write for bosons at the moment. Yeah, not write the general formula because I will repeat anyway for fermions later on when we have a fermions. For bosons, the consequence of the formulas, they were here, yeah, for the single particle basis. Yeah, because it's complete in orthonormal. This apparatus has a funny properties. So if I now take the commutator, bosons, therefore commutator. This commutator is delta R1 minus R2. This is a consequence of algebra of operators, in this case commutator of A's. So that's the only thing you have to commute. Yeah? If you calculate this commutator, the only things that you have to commute is these operators, A and A dagger. The rest is just complex numbers. We know they go out, yeah, of the commutator. And then what you end up with sum over nu, yeah, because the commutator gives you delta, nu1, nu2, so you have a single sum over nu. And this single sum over nu, you use the completeness of the basis, that gives you the delta function. Yeah, so. And the psi and psi dagger commute with themselves. So therefore this psi of R1, psi of R2 commute to 0, and the same for dagger. And this is because of this. Because the only thing you have to commute is A's. And A with A commute, and dagger with A dagger commute. So you get 0. So now we have this funny object. How we can now rewrite the operators. So the formulas are very simple. And most of you know this. But just to remind you. So now we start with the single particle operators. H1 would be transformed into, let me also remain the name, second quantization, yeah, add here, just to remind you, but then we skip it. Yeah? It's just a single integral, psi dagger R, and now your H1 R and psi R. Yeah? These formulas are for bosons and fermions. It's universal. Yeah? So you see what is left is just operators A and A dagger. Yeah? Because R you integrate out, so there's no traces of position, you integrate over. And yeah. So let me, okay, and H2, I write the general formula and then I give you examples. Yeah? And then we finally start with some physics. Yeah? So H2 transforms in a similar way, but now you have two integrals. Yeah? Because we have two variables here. So it looks like 1/2 integral dr1 dr2, and then we have psi dagger r2 psi dagger r1. Then we have our operator h2 r1 r2, and again we have two psi's. No, let me write it like this: 1 and 2, just canonically. Sorry that you have to correct in your notes. Okay, important to remember just to have the general formula for bosons and fermions. Yeah? For bosons, it doesn't matter where you write here R2, R1 or opposite, because they commute. For fermions, it's relevant because it gives you minus sign, because they anti-commute. So R2, R2, R1, R1. So it's the order of dagger, positions in dagger is sort of mirror reflection of the position. That makes actually Hermitian operator. Yeah? Because these operators, if you make Hermitian operator, you know A, B Hermitian is B Hermitian, A Hermitian. So this is clearly Hermitian form. Yeah. So this is the general formulas for bosons and fermions. So now I give you a couple of examples, yeah, and which we need, the operators we will need in the lectures. Of course, simplest I will do on the blackboard. More complicated, if you wish, you can either believe or make yourself. Yeah? So let me start with the, of course, in the end we need Hamiltonian. Yeah? Let's start with the Hamiltonian. Let's see what would be the second quantization form of our H0. Yeah? So now we have in the box, now let's go back to the box. Now we have these field operators. Yeah, so let me write here again, box. Yeah, which we don't have. So now nu is P. So we use this formula for H1 equals Laplacian, yeah, up to some factor. We have integral. Okay, let me this integral. So here let me have P1. I don't want to write this integral again with just this being Laplacian. Yeah? And here I will have P2, or better P2 here, P1. Yeah? So I just have to put this expansion in terms of the sums. Yeah? And P2 and P1 simply means which variable belongs to which psi. Yeah? So I will have sum over P2, P1. Yeah? And then I will have one of the volume. Yeah, because each of them has one of the square root of volume. And then I will have integral. Okay, then I will have these operators. Because they are position independent, I can take them out of the integral. Yeah? And now I have finally the integral, dr. Then I have from the psi dagger, I will have e to the minus I over h bar p2r. Yeah, this comes from this one. Then I have minus my operator. Each one. And now I have the position dependent part of my psi. Yeah, which is again a plane wave. So now I have to act. This operator acting on this gives me, of course, exponent is this will just be h bar squared over 2m p1 squared times the exponent. Yeah, because it's actually eigenfunctions of my single particle Hamiltonian. Yeah. So this again position independent I'll take out. Yeah. So then I continue here. So therefore what I get sum over P1, P2, P2, sorry, wait, P1 squared. P1 squared over 2m, 8P2 dega AP1, and 1 of the volume integral over R e to the I over h bar, or minus, let's say, P2 minus P1 times R. And I guess your intuition tells you that this integral should be simple. Yeah, because just a plane wave, you integrate over the entire space. And the answer for this integral is, if P2 equals P1, remember they are in the big box, they are discrete variables. Yeah? Of course, in the continuum, you know, this is kind of delta function, Dirac delta function. But working with this Dirac delta function not always convenient, so putting things in the box and then let the volume to infinity, it's a kind of more physically right strategy that does not involve you in all these mathematical complications. Huh? So let's figure out what's the answer. If P2 equals P1, exponent is 1, you integrate over entire space of 1 gives you volume. Yeah? If P2 not equals P1, yeah, they are different, you integrate very oscillating function. Oscillating function over very large distance. So of course you would expect in this case something 0. Yeah? So therefore the answer for this integral is just this one. Volume times, in our case, Kronecker delta, because we have a discrete set. So therefore only one p is left in this sum because they have to be the same. So therefore let me call it P1 equals P2 equals P. Yeah. Volume cancels. So what you get here is sum over P. Okay, let me write it epsilon P. AP dega AP, where epsilon P is, of course, P squared over 2m. That's trivial answer. Yeah? In a generic case, you can do the same exercise. You will get sum over nu epsilon nu a nu dega a nu. So it's similar story. Just very generic case. Another single particle operator that I will need is a momentum. Yeah, it's this one. You see, it goes completely in the same way. Yeah? So now instead of this, I will have this minus I h bar gradient. Yeah, let me do it in a different color. Yeah. For the momentum, I will have minus I h bar gradient. And this gives me simply P1. Acting on this plane wave, it gives me P1, because it's, again, this plane wave eigenfunctions of momentum. So therefore, I will have here P1. The rest is trivial. Integral is the same. Yeah. So the answer for the momentum operator would be therefore sum over P, P times AP dega AP. Yeah. And I forgot to tell you, but I guess you know this second quantization. So these operators, generically, this a nu dega a nu, this operator actually the number operator. It counts the occupation of the state nu. In our case, it's NP. Yeah, so I can write both of these formulas in the following way. Here epsilon p np, and here is just sum over p p np. You see, and this is actually, you see that the second quantization is actually is a kind of bookkeeping. Huh? So what we do here, how operator acts on the states. It counts the occupation numbers in a given state, multiplied by the corresponding quantity in the state, p or epsilon p, and sum of all states. Very simple bookkeeping. Yeah, and it's advantage of second quantization, so that it works and helps to work this way. So now, as an answer, I give you the answer. I don't want to spend time on writing all these lengthy formulas. But now let me write down the answer for the interaction. Yeah? if you try and failed or whatever, you can ask me later on. So now the interaction part, second quantization, or the same as very often we will use H interaction, second quantization. Here, this is this double integral with a plane wave. So what you get would be the following. 1 over 2v, yeah, 1v will remains. So here it cancels. It will remains here. Sum over P1, P2. I write two forms. Maybe one would be easier recognized for you than the other. And then you have A, P2, P1. Dagger P1 plus Q and Q. Sorry, P1, P2, and Q. This is kind of easy recognizable form. A dagger P2 minus Q. A P2, A P1. And now comes V tilde of Q. And V tilde of Q is a Fourier component of our interaction. So remember, it's R1 minus R2, so it's just the same. So this was, initially that was R1 minus R2. That is the answer. And I write in a, so that's why we still have 1 over V. Yeah? Because one integral hits this d of r and gives you something. Yeah? Sorry. Another way, which you probably will get from the very beginning, is the following: 1 over 2v, sum over p1, p2, p3, p4, under the conditions that p1 plus p2 equals p3 plus p4. And you guess what it is. It's momentum conservation during collisions, total. Yeah? And then we have similar structure, AP3, dagger AP4, dagger AP2, AP1. This is our operators. And now comes the amplitude, which is exactly now P3 minus P1. It's equivalent, please. I just solve this constraint in the following way, that I say P3 is just P1 plus Q, and P4 is just P2 minus Q. Then it's how these two forms are related. So just, yeah. So this comes similar to this one. Yeah. The other, so in deriving the formulas, of course, you have to go from center of mass and relative distance variables. Yeah? And over center of mass, you can always integrate because it's translation invariant system, and it gives you this momentum conservation, total momentum conservation conditions. And on the relative distance, it's exactly here. It remains. Yeah? So this is kind of interaction part of the Hamiltonian, yeah, which we'll deal with. So now you can ask me, what is the advantage of having these ultra-cold gases, yeah? Low energy scattering. Then, of course, we know if we model our potential, initial potential with the delta function, the Fourier is just a constant in front. Yeah? For this V of r in the form G delta function r minus r, of r, where I is r1 minus r2, I have V tilde q is just G. No Q dependence. So it would be the most simple case. And up to first order, I write it specially, first order, this is 4 pi h bar squared over m as. As is to the first order. So this is quite, well, much simpler form. If we now put this G here, yeah, And just to remember all this and to have again this understanding of the second quantization as a kind of simple bookkeeping, we can just have a look, present these terms pictorially, yeah, which is Feynman sort of diagrams and whatever. So what this interaction does, yeah? It annihilates particles in the initial. What happens with the scattering? You have initial states, two particles, P1, P2, they scatter, and the outgoing particles with the different momenta, P3 and P4. Yeah, that's exactly what happens here. It annihilates the particles in the initial states, yeah, and creates in the final states. It's exactly the scattering process. Particles which were initially in the quantum state with momentum P1 and P2 are not there anymore, yeah, so therefore they are annihilated. But then they are scattered to the different positions, to the different momenta, P3 and P4, so therefore they are created there. It's a very simple picture, and pictorially you can write it like this. Initially you have P1 and you have P2 that scatters. One of them goes into P3, another goes into P4, yeah, and you have total momentum conservation of total momentum. Yeah, and here there is this transferred momentum Q that goes. Yeah, so therefore this is just P1 plus Q, and this is just P2 minus Q, and the amplitude of these processes is just V tilde on Q. So it's a very simple pictorial picture of the interaction, a result of the interaction, in this case scattering, or always scattering, in the second quantization. Yeah? So time goes this way for some strange reasons. It's traditionally. Yeah? No. Because you write evolution operator, so initial state, and then on the left comes the final state. So that's why in all these pictures time goes from right to left. Okay, so this is this sort of simple final block, Feynman block for this case. So now I think I have everything. So let me now summarize. So the Hamiltonian for the ultra-cold bosonic gas would be like this: sum over P, epsilon P, AP dagger AP, plus G over 2V, sum over P1, P2, and Q, AP1 plus Q, dagger, AP2 minus Q, dagger, AP2, AP1. This is our Hamiltonians that we work with for the rest of the lectures. For fermions, we will need to add here some spin index, but the structure is exactly the same. Yeah, so this term would be a bit more rearranged in different ways, etc. But the general structure is like this. And this is kind of contact interaction. Again, be careful. Be careful. It's only up to first order. To higher order, you have to do something. Yeah, but otherwise, this is the simplest interaction form you can imagine. Okay, so now I have 15 minutes. And if the organizers allows, today we are very narrow. We have a narrow gap to the lunch. So maybe afternoon we start 15 minutes earlier. Yeah, or somebody plans to do a huge hiking or whatever. I hope it wouldn't be, yeah, because in principle I have quite a lot of materials and I don't want to sacrifice some stuff. Yeah. But test was important. So I can now get rid of the mask. Okay. Okay, so of course now I want to start with the simpler case because it prepares you for the rest for the bosonic case. Let me start with this one and explain why BEC is not identical to superfluidity in the end. Of course, it's a nice phenomenon with a lot of interesting things, but BEC is not the same as superfluidity. That would be actually, yeah. So ideal Bose gas. again, we have n particles, volume V, yeah. N over V is concentration which is fixed in the thermodynamic limit when N and V goes to infinity in the end. Yes. Standard, our standard assumptions. In the Hamiltonian, it's just sum over P, epsilon P, AP dagger AP. And of course, another important Hamiltonian is just number particles, number operator, right? Which is, of course, quite easy to write, which is just sum over occupation numbers in all quantum states, yeah? And typically, these two operators commute, yeah? You can very easily check that this H, okay, commute with N. So you can diagonalize it simultaneously, meaning that, okay, you are looking for the ground state of n number of particles, etc. So I don't want to go to a very detailed, just use, I guess, the result that you all know what happens in this case. If we are sitting at some temperature T, yeah, could be 0, but typically non-zero, yeah. So we know what is this, and then of course you're not your state is described by some density matrix, thermal density matrix, yeah? And we know that this average of these operators over this state, which is just particles number operator with momentum p, is given by Bose-Einstein distribution, right? So you have 1 over E epsilon p minus mu over t minus 1. Yeah? Where mu I find from the conditions that a number, of course, sorry, I'm skip a part that I don't want to work with a microcanonical ensemble with a fixed n, which is very inconvenient. So I go to canonical ensemble, introduce your chemical potential such that my n is fixed on average. Yeah, so standard sort of thermodynamical considerations. Yeah. So therefore, yes. So first of all, what is important looking at this formula, that you see that your chemical potential mu. Yeah, this is chemical potential. Mu is always non-negative. Epsilon p, let me write it just to have it in front. It is non-negative, right? So if I would have positive mu, then for some range of momenta, I would have this exponent being equal to 1, exactly when mu equals for this p where. And then I have singularity. And even worse, if I take the smaller momenta than p, then my np becomes negative, because then exponent becomes less than 1, which something like negative probabilities or so. Okay. Yeah? So this is ideal Bose gas. Ideal Bose gas. This is important. Ideal. For interacting, no problem to have positive. It will be positive. But for the ideal Bose gas, you always must have negative nu. So therefore, it would be convenient for me to write it for many reasons, either like this or like this. Yep. Minus mu, and mu is negative, is plus modulus mu. So that clearly tells you that this exponent is always larger than, or at least equals 1. Yeah? So let me now go to my particles number condition. Yeah? I know that I have to fix n. And if I follow these rules, yeah, so that means I have a sum over p AP dega AP, it should be fixed. Yeah, but yeah, I should probably write you before. So now we will write. Now we take the you know this trick how to go to this summation of a P in a very large box to integration of a P. Yeah, there is these rules. I can try to justify it, but it's very standard. It uses kind of semi-quantization rules in the box, etc., etc. So whenever we have sum of a P, when we do particular calculations in a very big box, yeah, when we just, although we know it's a discrete, but we think it's continuous distribution of P, it's always a rule. Yeah. So following these rules, it's just volume integral over P, 2 pi h bar squared. And then we have this distribution number. Yeah. So this we always have to fulfill, and it's condition for mu. So this is condition for mu. So now, of course, you know the story afterwards. Yeah, what happens with the BC. Let me tell you maybe not very canonical story that you find out in the textbooks, but historical story. How Einstein came to these conclusions. I guess his papers, I don't remember the exact title, but it was something like limited capacity of the Bose-Einstein bath or reservoir. It was something in this way. So what he looked for is whether we can always find mu or not, following these rules. Yeah? And traditionally what you do in the textbooks, you fix n and you start decreasing t. Yeah? So originally it was different way. Let me fix, I come back to the traditional formulas. Fix t, n of, yeah, and v. Yeah? And let me now change n, adding more particles. I have box, I throw particles after particles in this box and see whether I can adjust my mu. Yeah? So let me start with some n. I go to the n bar, which is larger than n. Yeah? What should I do with this formula to adjust mu? Yeah? That's the only parameter they can adjust. And then you immediately see that if t is a constant, the only way you can increase the value of this integral, yeah, is to reduce modulus. That's the only way. Because this is fixed, the only way is to decrease mu. Yeah? Because you can very easily see if mu bar is modulus is less than mu, then what you have in the then these things, e to the epsilon p plus modulus mu1, mu bar divided by t minus 1 is smaller, yeah, than e to the epsilon p plus mu over t minus 1. And then you have in denominator something smaller, the fraction is larger, so the integral increases, right? Okay, so you put more particles, you have less mu modulus, yeah, but there is a limit, yeah? So because mu modulus cannot be smaller than 0, it's always positive. Yeah? So what Einstein did, let's strike the extreme case. Mu equals 0. Just let's see. So we have this then integral volume dp over 2 pi h bar cube 1 over e to the epsilon p over t minus 1. Yeah? And the question is whether this integral is finite or not. Yeah? And in 3 dimensions, let me write it explicitly, we have volume integral, we have integral over angles, right? Then we have integral over modulus p squared dp, right? And then we have our fraction e to the p squared over 2mt minus 1. And if I rescale, so this gives me 4 pi, yeah, because the rest is angle independent. Yeah, sorry, and I forget 2 pi over h bar cube. So what I get here, I will get v 4 pi 2 pi h bar cube. And then if I rescale, I write p is square root of mt, 2mt times x. Yeah, x is dimensionless. And this is, see, this is our pt, kind of, up to square root of 2. Yeah? Thermal momentum. If I rescale it, yeah, then it comes with this 2mt to the power 3/2, yeah, square root to the power 3, yeah, because of this p, dp and p squared. Yeah? And the rest is integral infinity dx x squared e to the x squared minus 1. This is number. And this number is finite. And I don't want to spend time to calculate this number, although I can show you a nice way. And let me just write down the answer. And the answer for this number is just with the square root of pp, yes, square root of p 1/4, square root of p, and then zeta function 3/2. And this zeta function is function from this number theory. The p is very often there. So zeta z is this sum, defined at least in the region of the convergency of the sum. So in our case, the sum is n to the power 1 over n to the power 3/2. There is no nice answer in this case, but there is some numerical value. So you see, and this is finite. So that means even in the smallest available modulus mu, which is 0, yeah, n is finite. Of course, proportional to volume, but okay. Yeah? So that means you have a finite capacity of your bath, bosonic bath. It cannot absorb naively more particles than this critical number. Yeah. But you can put more. Yeah? We are strong enough to put more. And of course, yeah, and this critical number, actually, you can combine all these things together. So let me write down this critical number. Such that maybe you recognize the more traditional formula. So this NC, let me divide by volume, such that it is this critical concentration that you can achieve. It is, I guess, this 331. Yeah, remember this famous 331 for the critical temperature. Yeah? And then, do I have it in this way? Okay. H bar squared over m. And then I have T. And I guess I have the power 3/2. No, wrong. Minus, I guess, 3/2. Huh? Let me figure out. No. No, I guess it was correct. And if I write here minus 3/2, and here minus 1. Yeah, then it's correct. So Tm, maybe I write it like this. M times T, I guess it's like this. So, okay, it should be that T is 331 h bar squared over m n c to the power 2/3. So the formula should give you this one. I can't so quickly figure out. I think I'm correct. Minus, I think, yes. No, I guess it's right. Yeah. So this is kind of limited capacity. Yeah, and of course, what happens if you have more particles? The answer given by Einstein, it goes to the state with p equals 0, forming what is called condensate. Yeah, and in the end, this state with p equals 0 would be macroscopically occupied. Yeah, macroscopical number of particles will be in the state, but the corresponding formula we get for the second lecture today. Yeah. So and then maybe okay. So let's finish for today because lunch. They don't want us to be late, and we probably also don't want to do it. Okay. Thank you for your attention. If somebody has questions, you can ask either now or afterwards. But yeah, but we start 15 minutes earlier. Yeah, is it okay? After
As Frank, but I think in principle, yes, we start at 3:15.
It's okay.
But Frankie will start first, so we just have to make sure Frankie doesn't.
Okay. Okay. We ask him.
But I think it's fine.
We ask him at the dinner. If not, we announce it during the lunchtime. Sorry, not at the dinner. During lunchtime. Okay. But let's start 3:15.
Questions somewhere?
Questions? Now I think this stuff known. There was a lot of okay.
No, later.
Okay. Now I guess second quantization, people are familiar, just want to put a proper angle, which I need afterwards, and the BEC, I guess you all kind of know. There are some subtle things that maybe I discuss last time or ask questions, but I think it's more or less familiar material for most of you. Okay, so I guess
Okay, lunchtime.
lunchtime.